Alright, welcome to a video on compound interest. So in this video we're going to look at compound interest formulas. We're going to calculate present value, understand and compute effective annual yield. So compound interest is interest computed on the original principal just like it was for simple interest, but we also accumulate interest on interest, meaning the interest that's been gained then is added to the original, and then that becomes what we determine the interest by. Not just the original principal, but the new total, basically. Like we're using A instead of P at each time we compound interest to determine how much interest gets added on. So there's our formula. If this is important that you understand this formula specifically, if we're doing it once a year. So we're only compounding the interest one time per year, not multiple times per year. It'd be a different formula if we're doing it if we're compounding more than once per year. But for just single compound interest, it looks very similar to what we saw last time, but just notice the t, the location of the t is now an exponent rather than it being multiplied by the r. Alright, that's the big important thing for you to see here. Alright, same thing as before. A is the future value, P is the present value, or the principal, whatever you want to call it. R is the rate. We're going to use a decimal form again, and then T is measured typically in years for all these interest type problems. Alright, so let's do an example. You deposit $2,000 in that same bank that we talked about with the simple interest. Our rate's 6%, and we want to find the amount of money in the account after 3 years if we're using compound interest. Alright, again, assuming only compounding once per year. So we just plug into the formula. So our P is principal. So that goes right there. So that's where the 2,000 is coming from. The R is 6%, so 0.06. So 1 plus R, so 1 plus 0.06. And then, excuse me, and then T is 3, right? 3 years. So we're plugging that in up there. Right? And then just literally you can type that in on your calculator just like that as you see it. If you have a scientific calculator, that'll handle order of operations. So I get my calculator staying on the screen. So I just type in 2,000. Let me clear that out. 2,000 parentheses 1.06. Alright, and then this symbol right here is the caret symbols for exponents to the third power. Alright, and there's where that answer is coming from. Rounded to the nearest decimal place. Alright, part B wants us to find the interest. Remember, interest is what was added to the original deposit. This is a savings deposit, so it was added to the original principal to give us our total amount that we just figured in the last problem. So this is what we got in the last problem. Okay, the original principal was 2,000, so we can see that 382.03 is our amount that we gained from interest. So the interest on 3 years is 382.03. Alright, now here comes a new problem, a problem that a formula that I should say that we're going to see a lot of in this section, compound interest. Alright, we're going to see a lot of this R over N in this section and some sections to come. So what's going on here, the compound interest formula, if we're compounding interest more than one time per year, that's when we're going to use this formula. Okay, so the reality is this formula and the formula we used earlier is actually the same formula. It's just that in the original one we saw A equals P times 1 plus R to the T, N was equal to 1. So if you imagine N being a 1 here, well, if you divide R by 1, you get R, so it's like it's not even needing to be there. And then up in the exponent, if you multiply N, if it's 1 times T, you just get T. So we end up with just 1 plus R to the T, which is where we saw that formula before. So this actually is the same formula if we compound more than one a year, or if we just compound once per year. It's just n is 1, so we end up with r and t rather than r over n and n times t. Alright, everything else is the same. A is the future value, p is the present value, r is the rate, and n is the number of compound periods in a year. T is still years. Alright, so let's plug in and show how to do it. So we deposit $7,500 in the account, so that's P. We have a rate of 6%, so once again our rate is 0.06. Don't forget your decimal point to change these from percents to decimals, because if you left it at 6, that would be a huge interest rate. It would equivalently be saying 600% if you just left it at 6. Alright, and then we want to know if the interest is compounded monthly. If the interest is compounded monthly, then that's telling us that n is equal to 12. Right? Because there's 12 months in a year, and if it's compounded monthly, then it gets compounded 12 times. Alright, so we just plug all those numbers in, as it says down here, into the formula, and you see we end up with about $111.16. Sorry, $10,116.38. Again, you can just type that in directly, as you see it, 7,500 parentheses 1.005 raised to the 60th. Now, where's the 60 coming from? It is n times t, so 12 is n again, and t is 5. So if you go ahead and have that n times t multiplied out, you'll save yourself some trouble. Notice if I don't do that, if I try to do 12 times 5, hit enter, I get a much bigger number. Okay, and the reason is order of operations. It's multiplying after it raises to the 12th power. So notice if I put a parentheses up here in the exponent, it'll give me the right number. Okay, so be careful. Either what I would do is just go ahead and multiply the n times t together ahead of time, and then plug into the formula after you've already got that exponent. Alright, now after we rounded, we get our money rounded to near cent. Then again, to get interest, just subtract the original amount, and we get the interest on the account. Okay, remember, interest is the amount we added to the principal to get the amount that we ended up with after t years. Alright, continuous compounding. So we saw in the last example, we compounded 12 times a year. We compounded just every month. Okay, it's possible to compound weekly, daily. Most banks in the United States compound daily. They give you the interest every single day at the end of the day. You've probably seen those 2 p.m. Cutoffs to have your deposits in by 2 p.m. That's typically when they roll over to the next day and they accumulate interest. Well, it's possible to compound continuously. It's possible to break that day down into hours and compound every hour, or compound every minute or every second. But if you just keep breaking down the units of time more and more, you get to these just split seconds, that are almost immeasurable. And when we do that, we're getting towards what we call continuous compounding, where we're just always compounding interest. We never stop. It's a teeny tiny amount, because it's kind of like the idea of what we were doing before with this n going towards infinity, getting huge. And what happens is this little number that we add to 1 here, because the bottom gets so big, it's like we're virtually adding no interest, because that denominator gets so large. So anyway, instead of using this formula when we have a finite amount of compound periods like monthly or weekly or daily or even hourly or minutely or every second, that's still finite. But if it becomes infinite, or when we say in your homework it'll say continuous compounding, then we use a different formula. We use A equals PE to the R times T. Now if you have a scientific calculator, somewhere on that calculator you'll have an E button. Here it's above the LN button, second LN on this calculator. That's E to the power of, and that's what you use in this formula. Alright, now the way that I know that I'm using E rather than doing what I did in previous examples is because it says compounded continuously, whereas in the other part of this example and in the previous example it said compounded monthly. Alright, so we've got two accounts. We're going to put $8,000 in there, and we're going to pay either 7% compounded monthly, so 12 times per year, or 6.85% compounded continuously all the time. Alright, so there's the first one. This is the one that was compounded monthly, so I'm going to use the blue like I did before. So we end up with $12,160. Notice there's the 0.07 divided by 12. We don't see that E, that natural base number. Here's the other one, the 6.85%. So PE to the RT. So there's P, that was the principal, and then E is a number. Right, R is the rate written as a decimal. So that's 6.85%, and then T was the time measured in years, so 6 years. Okay, and we see we get $12,066.60. The other account we got $12,160.84. So it gave us a little bit more. It's hard for even if you don't compound nearly as much. We're talking about monthly versus every split nanosecond. It's hard to make up the difference in the percentages, even the nominal percents. It would have to be really, really, really close to 7 for that 7% interest compounded any amount, even though the other one's infinite. It would take a very close number to 7 to make up that difference. It's the rate that's kind of dictating things here. All right, calculating present value is a big idea. What present value is let's say that like down the road I want to put my kids in college, and I want to say, all right, well, what would I need to put in there right now, today, for it to grow for the 10 years or whatever it's going to take for the oldest one to start school? What would I need to put in there right now? What's the present value? What would it take to put in the bank right now into a specific account that's going to just grow at that rate, indefinitely, to be worth, $60,000 or whatever it would take to put them through college in 10 years? That's what this formula is for. It's A is still the amount down the road after 2 years, but P represents what I would have to put in now for it to grow to A in 2 years, okay, at that R rate, compounded n times per year. Okay, so it looks very similar to what we saw. And all you have to do is multiply both sides by this denominator. If I multiply both sides by 1 plus R over n to the n times t on both sides, it would cancel on the left, on the right, and it would give me that same formula that we saw before. And that's all we've done here. It's just divided basically this formula that we see from before. We've divided that thing by both sides by that 1 plus R over n to the nt, and we've got this new formula. So it's basically a new formula from an old formula is what we got here. Alright, but that's how you use it. Same thing. Everything means the same thing as it did before. It's just they're all in a different place. Alright, so how much should I put into account today if I'm getting 6% compounded monthly, and I want 20 grand in 5 years. I mean, I'm going to buy me a car or a big truck or something in 5 years, and I want to know what kind of deposit today, so I don't have to take out a big loan later on. So this is this is ideally how you could do things. If you don't have to borrow money, if you don't have to use up credit cards and take out loans, you actually save yourself a lot of money by planning ahead. It's just, of course, nobody gets to do that. But as we see here with this illustration, if we could save money at 6% rather than borrow money at 6%, it only takes us less than 15,000 to have 20,000 in 5 years to pay that thing with cash, rather than to borrow 20,000 and try to pay it off in 5 years and pay out way more than 20,000. So yeah, of course it's ideal, but hardly anybody can pull it off. But anyway, that's how we do it. You just got to be really careful when you put things like this into your calculator. Yeah, again, a good scientific calculator can handle all of these calculations, but if your calculator is not a scientific calculator, you're going to have to do it in order. You're going to have to do the order of operations on your own. So it's definitely worth your time to get a calculator that can handle order of operations. All right, so I can just type this in like I see it: 20,000 divided by parentheses 1 plus 0.06 over 12 close parentheses raised to the power of. Now again, I got multiplication down there, so I'm going to put 12 times 5 in a parentheses right down there in the denominator. Alright, so there's where that 14,000 is coming from. Just make sure that if you have a scientific calculator, learn to use those parentheses to get it to do what you want it to do. Alright, a concept called effective annual yield. So basically what that is most rates that you get from banks are actually compound interest rates, because it's going to be compounded in lending institutions if it's a loan. So you may be quoted like 5%, but you get something called yield because you are actually borrowing at a different rate as far as what's actually going to come out or what you're going to have to pay back. And what yield does is it basically simplifies it, gives you a simple interest rate, comparing it to what you started with, what you originally borrowed, or what you originally deposited if it is savings. That would produce the exact same amount of money at the end of a year as compared to the compound rate. So let's look at an example so you can see what I'm talking about here. So if we put $4,000 in an account, it pays 8% compounded monthly. So there's, again, we're using 12 for our N. All right. Now there's going to be other things that you see in your homework, like daily would be $365. If it were quarterly, that would be 4 times in a year. Annually is 1. Semi-annually is 2. But monthly, daily are the most common ones that we see. All right, find the future value after 1 year and use the future value for simple interest to come up with yield. So we're taking the compound interest formula down here, P times 1 plus R over N to the NT, and we're plugging in the 4,000 for P, the 0.08 for R, the 12 for N. And T is just 1 because we want to get yield. So we're just going to see what happens after 1 year. So we are at $4,332 roughly after 1 year. All right, now what we're going to do with that is we're going to plug that back into the simple interest formula way back from the beginning, where we solve for the rate, basically. If you remember doing that example where we solve for the interest rate. This is from your last section set of notes. So remember when we had A and P and R, or sorry, A and P and T, how long it took for P to grow to A. And we could plug in and we could solve for R. That's what we're doing here on this problem. We are we now know what the account grew to. It grew to this 4,332. We knew where it started. It started at 4,000. We knew the interest rate. We knew the value for t. It took 1 year, so we can plug all that stuff in, and we can solve for r again. So r ends up being about 0.083, which is 8.3% roughly. Right, rounding it to the nearest tenth of a place. Now another way you can get yield, this is another little kind of shortcut formula you can get yield. You can actually get yield, let me kind of blow this up. You can also get yield from just this part of this formula. If you leave off P and this T, you can get another method to give you yield. So instead of A, we'll call it Y for yield. And we just do the 1 plus R over N to the N, right? And then we have to subtract 1 to get a decimal. Doesn't look very good. Subtract 1. Okay, so on this problem, we were told that the interest was 8%, and it was compounded monthly. So that means in this formula we got 1 plus 8% compounded monthly raised to the 12 minus 1. And if we do that, alright, there's to the 12 minus 1, I end up with the 0.082999, and then times 100 to get it as a percent. So there's the 8.2999, which was 8.3 is what we said before. So there's an alternate method if you want to use that for yield anytime you get asked yield.